traveling at 17,500 miles an hour. In 8 minutes, the humans inside will no longer feel the pull of the Earth's gravity.
So space shuttle month used to take 8 minutes.
In that time, space shuttle had to travel 180 miles while reaching the final speed of 17,500 miles per hour. No one within those 8 minutes, not a single human being, was in charge of piloting the space shuttle. For everything to work out without a hitch and before the computers took over, every single aspect of motion had to be made predictable. So the question is, how did NASA make motion predictable?
Two, one, and liftoff. Liftoff of the 25th Space Shuttle mission, and it is...
But what started out as a grand achievement for NASA, 73 seconds later turned into a national tragedy.
Just because we got rockets doesn't mean that we're going anywhere. They were able to get only 73 seconds of predictable motion out of this.
Rockets aren't new. Neither is the idea of riding them to the heavens. One night in the 16th century, a Chinese nobleman, Wan Hu, prepared himself for liftoff. But then there was, as modern spacemen say, a glitch. And though Wan Hu didn't make it to the stars, he couldn't be found on the face of the Earth either.
You had the right idea, you need rockets. Except you gotta do a little bit more than that. You have to take something which is chaotic and unpredictable, and you need to make predictable motion on it. Motion that allows, predictable motion is the sort of motion that allows forecasting.
No danger, however, as the satellite's now expected to smash into Quasi, an uninhabited part of the Australian outback. Scientists say that...
So satellite is coming down. Do you know exactly where it's gonna land? Do you know when it's gonna land? How fast it's gonna land? And this guy's at the landing spot. So he's getting ready for impact. He's trying to cushion the impact using pillows. Motion is so predictable that he's not only is he ready for impact.
Do you Yahoo?
Notice that also his dog is also ready for impact. Nah, that's predictable motion. So how do you make motion predictable? It's an extension of the previous review. So how fast the velocity, it's measured distance over measured time is your velocity. It's a combination of speed and direction. How fast the velocity changes in time is your average acceleration, which is the same as speeding up, slowing down, or changing direction. Speeding up, that's acceleration. Changing direction is also acceleration. Alright, so you're speeding up and changing direction at the same time, so combination is also acceleration. Now something is about to happen to your acceleration. On impact, your acceleration is going to change. So changing acceleration in time, what is that called? One of you guys already mentioned how jerk the motion itself is called jerky motion. Prime example of jerky motion that we discussed so far is car collisions. Guys, at 40 miles per hour, crash testing, the impact lasts 10th of a second. Within 10th of a second, what happens to the crumple zone? It just crumples, right? As this crumpling, it goes through jerking motion, which means that the acceleration keeps changing. All right, because the acceleration keeps changing in jerking motion, we use the average acceleration formula. All right, so the prime example that we looked at is car collisions.
Before we get started, you may want to pull up preview 4 from Canvas. You may want to take notes on it. Let's do one more review, this time mathematically. So here's an object getting displaced in time. Measured distance over measured time is average velocity. Here's the velocity is changing in time. How fast the velocity changes in time is average acceleration. Measured terms are on the right. Averages are on the left. Now the acceleration is changing in time. This thing is within a certain time period. So this is known as J. J is jerking motion. So once again, the terms on the right are measured. The term on the left is average. So this is your average jerk. Example of jerking motion is car collision. During impact, the acceleration is going to keep changing, which is jerking motion, within 1/10 of a second. Maximum acceleration could be 120 Gs, while the average is about 20. So when there's jerk, we're interested in the average acceleration, not the maximum or the minimum acceleration values. Jerk can be eliminated by making the acceleration constant. So jerk can be eliminated by fixing the acceleration to a constant value. Usually displacement time, the acceleration is forward, the initial and final velocities. There are 3 formulas that will make motion predictable. X is the location, V is speed, so those are 2 things that become predictable. Location as well as the speed. The first formula is going to locate the object for us at any given point in time. Second formula is also going to tell us how fast the object is moving at that time. The third formula is going to tell us if you know the location, you will know how fast it's moving. So location as well as speed will become predictable. Let's take a look at problem number 2. Alright, so the space shuttle travels 180 miles while reaching the final orbital speed of 17,500 miles per hour. So at what acceleration does this happen? The first thing we need to do is we need to convert the British unit system to a metric unit system. And then we got 3 formulas to pick from. We'll make a decision as to which formula to use based upon our symbols. And the formula that has all the 4 symbols given to us is formula number 3. Isolate A from this formula. The initial speed is 0. Do the algebra. And into the final formula, we have to put the numbers with metric units. They need to be substituted in. So it's going to give us an acceleration roughly about 10.5 Gs. Roughly 10.5 Gs. That's what we got for the acceleration. So we know that it's going to take about 10.5 Gs to go from 0 to 17,500 miles per hour within a distance of 180 miles. 10.5 Gs. So here's a question for you. Is that too much? Can we handle 10.5 Gs for, what is it, 1.5 minutes maybe? Well, we know that the pilots can because they're subjected to a G-lock test between 7 to 12 Gs. We also know that John Stapp survived up to 20 Gs for a few seconds. So
he suffered no serious or permanent ill effects.
So the initial indications are that it should be survivable. So if our numbers are correct, if we set our acceleration to 10.5 Gs, it should take us 8 minutes to travel 180 miles while reaching the orbital speed of 17,500 miles per hour. But how long would the journey really take if we have a single fixed acceleration at 10.5 Gs? It wouldn't be 8 minutes, would it? Let's find out. So look at the formulas that has T in it, the first one and the second one. And either formula is going to give the correct answer. We will go with the second one because it's easier to use. Isolate T and then plug the numbers in terms of metric units. So it's going to give us 1 minute and 14 seconds. But in the case of NASA, it takes 8 minutes. So why is it that we end up getting only 1 minute and 14 seconds? Yeah, so that's weird. We were hoping to get 8 minutes, but instead we got a little bit over 1 minute and 14 seconds. Isn't this confusing? I think it is, because if a launch can carry out using a single fixed acceleration within less than 1.5 minutes, why waste so much time? What gives? Astronauts can handle 10.5 Gs, so we discussed that before, at least for up to 1.5 minutes, especially if they have G suits on. So what's the main concern here? What is it that we're not seeing? NASA would never set the initial acceleration to 10.5 Gs. Here's the reason.
The main engines create acoustic shock waves so powerful, their vibration would be enough to shake the shuttle apart before it ever got off the pad. To dampen these waves, at the exact moment the engines reach full thrust, 300,000 gallons of water are released into a trench below the shuttle. As the shuttle accelerates, massive stresses build up on its light aluminum frame. To prevent it from disintegrating, the main engines must be throttled back until the shuttle reaches thinner air in the upper atmosphere. When pressure reduces, the shuttle opens throttle, rocketing toward space at 3,000 miles per hour.
So NASA uses
2 minutes
stage
from launch,
rocket
the
boosters.
SRBs burn out and fall toward the Atlantic
to set the
Ocean.
acceleration to constant values at different stages, so that the mission takes about 6 to 8 minutes to complete. Each stage, the acceleration is fixed to a constant
52
value.
miles up, the sky goes quickly from blue to jet black. Traveling at 17,000 miles per hour, the roar and tremendous G-forces of launch suddenly vanish. This is MECO, main engine cutoff.